Auto land operation is activated when the mode control panel or MCP approach button is pushed. With the autopilot engaged, descending through 1,500 feet radio altitude causes the autopilot systems to be powered by separate sources, with 3 autopilots engaging. The left autopilot and captain's flight instrument transfer bus is powered by the left main system. The right autopilot and first officer's flight instrument transfer bus is powered by the right main system. The center autopilot is powered by the battery standby system. During an approach with the autopilots engaged between 1,500 and 200 feet, a generator failure causes the electrical system to reconfigure to its non-isolated state. Both bus ties close to cross-tie power to the opposite AC bus. The center autopilot reverts back to being electrically powered by the left main AC bus. Even though 3 autopilots are engaged, they are only powered by 2 electrical sources. The Auto Land Status Annunciator, ASA, changes to Land 2, no Land 3. During the approach with the autopilots engaged below 200 feet, both bus tie breakers remain open, causing the respective bus off light and both bus tie isolation lights to illuminate. The autopilot associated with failed AC bus is no longer powered, causing its switch light to extinguish. The Auto Land Status Annunciator, ASA, remains unchanged, displaying Land 3. Both flight instrument transfer buses remain powered. The automatic landing continues with 2 autopilots engaged. After the aircraft is on the runway and the autopilots are disengaged, or an autopilot go-around is performed, the electrical system reverts back to its non-isolated state. The electrical system provides various types of load shedding conditions to protect the operation of essential components. Different types of load shedding occur for the following situations: during engine start, generator loss, overload shedding. Before we describe the 3 load shed conditions, let's describe an automatic reduction of electrical demand that occurs before engine start. This condition occurs on the ground to ensure enough electrical power is available for essential equipment and occurs automatically. Some electrical components are simply inhibited from operating before the engines are running. Examples are the center hydraulic system number 2 electric hydraulic pump, the center tank fuel pumps. Other components are shed to prevent overloads from occurring. Electrical components are shed by priority until the loads stay within the capacity of the generators. Galleys are shed first, followed by utility buses. Thereafter, individual equipment is powered down. When another electrical power source is made available, the components are returned to electrical power in reverse order. There are 3 types of load shedding conditions. Engine start load shedding occurs when the APU is the sole power source for both electrical and pneumatic power during engine start. Both utility buses trip off simultaneously when the engine start selector is moved to ground for the first engine being started. Reducing the electrical load assures that enough pneumatic power is available to start the engines. When that engine's start selector returns to auto or its generator breaker closes, the utility and galley buses reset automatically. During the start of the second engine, only the utility and galley buses for that engine generator trip off. As the name generator loss load shedding implies, Loss of a generator during takeoff or in flight causes both utility buses and the galley buses to trip off. The buses can only be reset by making a second generator available, at which time they reset automatically. This generator loss load shedding protection feature automatically arms when throttles are advanced or the air-ground sensing system indicates that the aircraft is in flight. Depending on whether the failure is a simple generator failure or the generator failure occurred as a result of the engine being shut down, additional loads such as cabin ceiling lights and the respective center tank boost pump are automatically shed as well until a second generator is established. Overload load shedding electrical load protection is designed to protect the APU generator or external power cart generator from electrical overloads with a center or left hydraulic pump operating. In case of an overload condition, the galleys are shed first. There are no cockpit indications of galley shed occurring. If the shedding of the galleys does not correct the condition, the utility buses are shed next. If only the galleys tripped off, they reset automatically when the electrical load is reduced or an engine-driven generator comes on the line. If the load shedding progressed to the utility buses, they will have to be reset manually by cycling their switches to off and back to on.
The main DC electrical system uses transformer rectifier units, or TRUs, to produce DC power and are powered by the main AC buses. The main DC buses share a DC bus tie breaker located in the DC bus tie. The DC bus tie breaker is normally open and closes only in case of failure of the associated transformer rectifier, or TR, or AC bus, and then only if both AC bus tie breakers are in auto. The left main DC bus normally supplies the battery bus and standby DC bus.
In case of a complete failure of the AC generating system, including the hydraulic-driven generator, the aircraft electrical system is reduced to the aircraft battery for its sole electrical power source. This battery standby power system includes 4 electrical buses and an inverter that converts DC power to AC power for the standby AC bus. The battery standby power system includes these 4 buses: hot battery bus, standby DC bus, standby AC bus. Now, let's describe the purpose of these buses. The hot battery bus supplies power to systems that need continuous electrical power. Items that are powered by this bus are listed in the box. Before APU, external, or engine generator power becomes available, the battery is the power source for the hot battery bus. With APU, external, or engine generator power available, the battery charger is the hot battery bus power source. Before generator electrical power is available, the battery bus can be powered by the hot battery bus through the battery switch operated battery switch relay. With the battery bus connected to the hot battery bus, the battery discharge light illuminates, indicating that the relay is closed. The battery bus powers a number of items. Some important ones are listed in the box. If the battery switch is not on after generator electrical power is established, the battery switch off light illuminates and ICAS will indicate a battery off advisory message.
Before generator electrical power is established, the standby AC bus is also powered by the aircraft battery and the standby inverter through the standby power switch auto or battery position. Some of the important items powered by this bus are listed in the box. After generator electrical power is established,
The left AC system, through the left AC transfer bus, powers the standby AC bus. If the standby AC bus should lose power, the standby bus off light illuminates, and ICAS indicates an advisory message of standby bus off. Before generator electrical power is established, the standby DC bus is powered by the aircraft battery through the standby power switch auto or battery position. Some of the important items powered by this bus are listed in the box. After generator electrical power is established, the left DC bus is the principal power source for the standby DC bus, with the main battery operating as a backup power source. If the standby DC bus should lose power, the standby power off light illuminates, and ICAS displays the advisory message of standby bus off. A battery switch located on the overhead panel provides electrical power to some annunciator lights and to start the APU while on the ground when no other electrical source is powering the airplane. The battery also supplies power to the standby and battery buses whenever AC power is lost on the ground or in flight.